last minute. Hi, Tanguy, Nicholas, Ken, H. All right, so we're starting. First of all, I need to remind everybody that there is a Best Paper Award where you can win oodles and oodles of money. Not really. You win the accolade of everybody here at DVCon. Please vote for papers. The papers are in the virtual sessions. You can vote, and you need to vote pretty quickly because in 2 hours we're presenting a half an hour after the session. During that half an hour between this session and the voting and the presenting, they're doing the tallying. So please vote for papers. These guys put a lot of work. These people put a lot of work into their presentations, and we should tell them how well they did. So we will get started. The first paper is, hang on, need to get to it. I had it up and then I went over somewhere else. The first paper is Extensions of PowerWare IP Reuse Approach to ESL. The presenter is Antonio Genov. Antonio is a systems engineer in architecture modeling at NXP in France. In 2021, after 3 years of research, he defended his PhD, congratulations, on the subject of the creation of power estimation framework based on SystemC TLM performance models of SoC interconnect and memory systems. He has several papers related to his research in DVCon Europe and other academic conferences. Please, everybody, welcome Antonio Genov's presentation.
The topic of the paper that I will present you today. Hello, everyone. My name is Antonio Genov, and the topic of the paper that I will present you today is related to the extension of power modeling capabilities to system-level models, and more precisely to the creation of power-aware reusable IP models. This is part of my studies during my PhD degree. Today, I will briefly present you one major flaw in the current power analysis approach, and I will talk about the initial implementation of one power estimation methodology that can be applied at the very beginning of the SoC design flow, and that can enable the reuse of power-aware deliverables in multiple platforms. Then I will introduce to you our proof of concept evaluation bench. Currently, the power modeling using formats such as UPF is initiated at RTO level. Thus, the power intent optimization is started only when the RTO model is ready, which is significantly late in the design flow, and major effort and financial investments were already done. So this stage, falling to a bug related to power glitches or passing the power budget, can bring to important additional costs. Moreover, the simulation time of these models is tremendous and still limited. Since at system level, the power waste can be considerably reduced thanks to the right choice of components, it is meaningful to add power-aware simulation capabilities. At early architecture definition stage, it is difficult to predict power consumption. At this stage, architects are swapping between calculation specifications and manufacturer documentations in order to find power metrics, allowing to estimate some power profiles. The possible outcomes from this approach are limited to maximum and minimum power consumption without considering specific complex use cases. The solution we propose is based on the power modeling and estimation library called Power Clock Arc. Power Clock Arc is a SystemC C++ library developed in LIAT laboratory for power estimation at system level. This library is based on the UPF standard semantics, but abstracted at the TLM level. It includes components such as design elements containing the power computation for each functional module, power domains, power switches, supply nets, and the power state table identical to the UPF one. Since there is no current standard for the description of clock domains, Power Clock Arc introduces a methodology that allows us the insertion of clocks, clock domains, GPLLs, and a clock state table identical to the UPF power state table. A power and clock specification is built on the GPLLs to define the power intent. This way, the separation between the hardware and the design and the power clock intent is reinforced. The definition of power intent and the use of operating performance point table based on the one used in the Linux kernel allows us to define power management strategies such as clock gating, power gating, DVFS, and others, which are then automatically controlled by a power management unit or PMU module. Power Clock Arc allows us to maintain the separation between the functional model and the power intent. This means that there is no intrusive power-related code inside the functional model, allowing it to be reused for performance estimation and making it more readable and efficient. We can observe the influence of each energy management strategy on the performance of the model. For the power state transitions, the initiator module are sending simple commands updating the OPP table to the PMU, which automatically apply all required conditions and modifications. This study was done on NXP SoC family platforms, and the proof of concept was executed in 3 main phases. First, we have created from scratch a reusable timing-aware behavioral model of a switch matrix interconnection subsystem used in the IMX8 QuadMax from NXP. We have described and calibrated its power model, and we have correlated the results from our simulations with our silicon measurements on the same use cases. In the second phase, we have executed a very important test on the interoperability and the portability of the power model. We have directly reused this reconfigurable and already calibrated in phase 1 model on another existing NXP SoC called IMX8 QuadXP without modifying the power parameters. Then we made the correlation again with silicon measurements to prove the power estimation accuracy of the new bench. In the last phase, we have reused again the model on another higher performance SoC, which is in its very first stages of development, to prove the utility of this kind of analysis. Thus, we were able to extract power estimations for specific use cases during the design specification, which is long before the creation of the RTO model. In order to start the modeling and the proof of concept steps, we had to choose very carefully the granularity, the abstraction, and the portability of functional modeling approach, because at system level, we are very limited in terms of time and resources. We have created basic skeleton modules allowing to keep uniform structures for all blocks, which are well adapted for continuous refinement. In order to create reusable, clear, and configurable interfaces, and to avoid any protocol-specific code in the behavioral description, we have separated the communication part from the behavioral part and created reusable communication interfaces. These interfaces allows us to implement the protocol specifications externally in a derived specification, and we can use them to create and test different communication protocols and third-party provided ones without significant or any changes to the behavioral model. This is a common functional modeling approach. The main components tested here are based on the IXI communication protocol. Therefore, we have modeled its main functionalities with some abstractions because we have targeted specific IXI features which have direct influence on the power consumption of the chip. So yes, we have described the power intent and management for the IMX8 Quad Max using the previously presented power clock arc methodology. It contains about 1 voltage domain with low power support, about 5 power domains, and more than 25 clock domains with enabled hardware automatic clock gating mechanism. Since the power model and the functional model are separated following the semantics of UPF, the functional model must also contain the configurable PMU module provided with power clock arc, which contains the power and clock state table, manage the power and clock changes during the simulation, and most importantly for us, it makes the connection between the power and behavioral models. In order to eliminate the power code of the traffic generators, we have defined the master module that controls the OPP state changes. The couple master PMU represents a very simplified version of a real IP from the IMX8 chip controlling the power management policies. Considering that the power models are separated from the behavioral ones, we can easily change them and execute what-if tests. And moreover, they can be easily reused together with the IP model or for similar hardware structures. Since we started the development of the SystemC TLM functional model and the power clock arc power model in parallel with the development of the IMX8 Quad Max, which was in the medium to final production phase, we had a test version of the silicon and an initial power measurement curve of the silicon containing information about the power consumption for several important states of the SoC. Using the measurement curve presented here and the information about the cell count of each unit, we were able to extract the power model parameters and more precisely the leakage resistance and the low capacity values. As first approach for the activity values, we simply used 1 for active with transactions, 0.7 for active without transactions, and 0 for inactive. Later, we were able to refine these values thanks to the toggle rate and the CPM data coming from the backend teams in order to have more realistic values. Here we show a simulation of the 2 major test cases. In the first test case, we have only 1 active traffic generator playing the role of a processing unit executing memory accesses. A 4K interleaving in the switch matrix interconnection subsystem ensures the optimal memory usage. As this is a relatively charged traffic, there is always at least 1 active memory. The spikes come from the interleaving between memories and the activity of the modules. In the upper figure, we show a comparison of a simulation with our circuit power management strategy and another with a not optimal power management. We can see that the power consumption is at least 2 or 3 times lower with the power management strategy, which just proves one of the interests to have this kind of power analysis at early stage of the design flow. Similarly, in the lower figure, we have a display refresh use case simulation. And I'm not entering into the detailed analysis here, but we can extract the same conclusions. For the power consumption correlation, we have used power measurements extracted with the Bay Libre Acme board for power measurement, and we have controlled the temperature with the MaxTC temperature forcing system in order to keep a stable ambient temperature. We have extracted measurements for the same use cases as the ones executed in simulations, which were a memory copy and display refresh. The measurement resolution of the tools, and maybe all the tools on the market, is much lower than the simulation ones, and it is not possible to observe the detailed power profile. For this reason, we have extracted the measured values and we have calculated the average power consumption. We did the same thing for the results from our simulations and we have correlated with them. The results from these correlations were very promising, turning around 85 to 98% correlation depending on the tested use cases and measurement conditions. In order to increase the correlation accuracy, we found a way to extract higher resolution measurements using National Instrument Data Acquisition hardware, and we have created a LabVIEW model allowing the extraction of voltage, current, and power consumption. We have configured the system to 1 million samples per second, and this resolution is still a lot lower than the one from our estimations, but it is better than the previous one. We can see more clearly some of the power profile variations, for example. The functional, power, and IP-specific libraries of reusable units that we have created allowed us to easily model another platforms. These modules were reused for the definition of the IMX8 Core XP platform, which has a similar structure, but with less subsystems and interconnection paths and algorithms, only one DRAM memory, a lower clock frequency, and less clock domains. We have executed the same use cases on it, and again, without entering in deep detailed analysis here, we can see that the behavior is a bit different than that in IMX8 QuadMax, which is expected. During the memory copy use case at left, we only have one active memory and almost constant activity without spikes, because there is only one external memory. What we cannot see here because the scales are hidden is that the power consumption is almost half the one of the QuadMax, again, due to the single memory structure, the smaller switch matrix interconnection block, and the lower clock frequency. The total power correlation with the measurements executed using Bay Libre is about 90%. Using the same approach and combining the reusable units, we have modeled the new generation IMX8 SoC platform. The structure is a bit more complex because it contains more subsystems, but the major part of the units are included from these libraries. The number of design elements and clock domains are almost doubled compared to the IMX8 QuadMax, so around 40, such as the clock frequency. It's also doubled. the supplied voltage is reduced. On this slide, we show a comparison between the power results for the three platforms. We can see the increased performances and lower power consumption of the new generation platform compared to the previous ones. On this figure, we can see that the transactions execution is almost 2 to 3 times faster in the new generation platform than that for the other two platforms. Of course, this is mainly due to the higher clock frequency when we compare it to the Quad Max and the two external memories when we compare it to the Quad XP. On the right figure, we can see that the energy consumption is also significantly reduced. Since the display refresh time is fixed by the refresh rate, we can see how the faster execution of the next generation platform is reducing the energy consumption to a level that it is less important than the energy consumed with the single memory structure of Quad XP. So this slide showed the part of the analysis of new generation platform that we were able to make and present using this approach. The final deliverable is a combination of configurable and reusable IP model plus one or more power intent files plus one or more configurable power management files plus one or more configurable master modules and configurable PMU modules. The master module can be replaced with user-defined one because the power management strategy can be defined different for each device. It can be reused as a library if we do not need to execute additional hardware or power-related modifications when the power-aware IP is reused. Of course, we can have only the IP model as library or only the power model or both together. Since they are separated, we can have different configurations depending on what we consider sensible information and what can be opened and configurable by the final user. So we have shown that using the right modeling strategy from the beginning allows easy reuse and fast turnaround time when porting the model from one device to the next one. We gave an example of applying this strategy on a complex switch matrix interconnection subsystem with realistic test cases. We use this approach to estimate the power consumption of the NXP next generation high performance SoC and reusing the power-aware IPs with power clock arc has allowed us to significantly reduce the development time of two new architecture models and increase our design space exploration capabilities. With this approach, we were able to create two new derivative architecture models and execute this critical analysis in just over a week, around 8 times faster than without the power-aware IP reuse. Thanks to this approach, power constraint and optimization are introduced at earlier stage in the design cycle, where capturing a performance and power problem can significantly accelerate the design flow. This work is the first to focus on demonstrating the portability and reusability capabilities of this library. And of course, it is just an initial step. So yes, this is the end of my presentation. Thank you for your attention and I hope that you enjoyed it. And I'm here to try to answer all of your questions. Thank you again.
Antonio, if you can unmute and turn on your camera, sir.
Yes.
He's joining us from Germany, right? No, France.
France.
So
Yeah.
France. So it's really late for him, guys. So give us some questions. But Shweta has a question for you. Are these model simulations benchmarked against the power-aware sims in DV?
Yeah. Okay. So here the comparison was made only with measurements from real silicon. Unfortunately, for these platforms, we don't have the performance models with the RTO or with all the test benches. So it was kind of difficult to benchmark it against the RTO. At NXP, at RTO level, we are really limiting our power tests at the maximum, at the corner cases, at the maximum values and the minimum consumption. So it is difficult for us to benchmark it against that.
Okay, sounds good. Does anybody else have any questions? We have about 4 minutes for Antonio. You can even unmute yourself and ask the questions live if you prefer, if typing is not your first language.
Maybe here, Juan. Antonio, I'm curious about are you working with pure SystemC, so you are taking the libraries and coding directly, or are you using some IDE for this prototype?
Sorry, I can't hear very well.
Oh, sorry. Now?
Now it's better. Yeah.
Okay. The question was, are you using directly the SystemC library? So encoding from this, or are you using some IDE for the prototypes and the modeling phase?
Yes, for this I am using only SystemC. I'm not using the third-party libraries, but they can also be used with the PowerPoint. There is no problem with that. When you are telling where I'm talking for a third-party library, HTML or ICC. So we did some experience, some tries, and it can work with them.
Okay. Okay, great. Thanks.
Anybody else? Well, Antonio, I thank you for taking the time for recording this and all the work and writing the paper and presenting here at DVCon and staying up late to answer our questions.
Thank you also to
unless you're a late person. I mean, you might be one of those people that works, but thank you so much. And in a minute here, we'll move on to the next question. Unless somebody has another question, come on, anybody?
Last chances.
Last chances. Everybody's real quiet. They think we're in like the library or something. You must have done a really good job, Antonio. Everybody understood everything you said. And it was crystal clear. Well, thank you so much again. And we will get ready here to move on to the next presenter.
Okay, thank you.
Thank you. Have to wait 30 seconds, guys. All right, our next presenter, Shweta Saxena, I'm sorry if I mispronounce, has a bachelor's degree in electronics engineering and has been working as a design verification engineer at Analog Devices for the last 6 years. She previously worked at ST Microelectronics. Her presentation is SystemC virtual prototyping, ride the earliest train for time to market. Everyone, please welcome Shweta's presentation. Thank you.
Hello, everyone. A very good day to all of you. My name is Shweta Saxena. I work as a design verification engineer, and my co-author, Mahantesh Danagouda, works as a system engineer at Analog Devices. Today, I'm going to talk about the SystemC-based virtual prototype, or VP, as it is generally referred to. We developed this virtual prototype to help in early hardware-dependent software, or HDS development. HDS notably consists of device drivers and boot code. Using this VP, we gained a 3+ months head start in the software validation schedule, thereby aiding pre-silicon validation and hence positively impacting our time to market. So let's begin. Now, what is system virtual prototyping and where does it come into picture? When beginning the product development, we start with defining the system, following which comes the system design, the subsystem design, and the initial system verification. Now focus on the blue region here. This is the initial product development time, which can be used to accommodate elaborate software development, its validation, and architectural evaluation. But that is not the case traditionally, since the software development and validation methodologies that are currently put to use are available only after the design is developed up to a suitable benchmark. The software development cycle then begins in unison with the rest of the design cycle, which would be physical system verification, system manufacturing, commissioning of the system, and eventually system maintenance. To understand this better, let's review the common software development methodologies, namely RTL simulations, hardware acceleration or emulation, FPGA prototyping, and finally, software development on silicon. Now, all these methodologies are only available a certain amount of time after the product has been defined, which means very well into the design development phase. Now, this time could range from 3 to 6 months or more, depending upon the design complexity. We identified this gap, and this is where a virtual prototype comes into picture. Now, the software folks usually cannot make much good use of this time. So a virtual prototype can make a big impact here. It is available early in the design cycle, and the models run at near silicon speed, which makes it a good option for software development where system timing accuracy is not a concern. A quick comparison of different methodologies with respect to virtual prototyping shows the RTL simulations, although accurate, are extremely slow as compared to virtual prototyping. As per hardware acceleration, there is no analog modeling feature available, and its interoperability with software is also challenging. On the other hand, virtual prototype supports good modeling, analog modeling features, and hardware software debug is much more easier. With FPGA prototyping, we get real validation, but the hardware debug is a big challenge, and most of us know that. Virtual prototyping supports software-driven verification. Now, coming to the software development on silicon, it comes at the end of the design cycle, and it is pretty late for beginning of the software development. Although it provides real-time validation, the hardware debug is much more challenging. On the other hand, virtual prototype being available earliest in the design cycle can make a big impact on the time to market. As we progress towards silicon, we see that the speed of the simulation improves, but the hardware debug becomes more and more challenging, and the visibility into the design also degrades. So we identified and addressed the software development and validation challenges and put the initial product development time to good use. Statistically, time and effort that is invested in the HTS development ranges from 3 to 4 months or even more. The software team is blocked for validation until the FPGA is set up, which will only happen once the RTL is frozen. So that means we lose on initial project development time. With the FPGA, hardware accelerators, and silicon, limited boards are available. So the software team has to make judicious use of these resources. As for the validation challenges, the UVM and system Verilog code is difficult to navigate for a software person and debug too. Besides, it does not offer a straightforward reusability to the software teams. So our proposed solution to these challenges was creating a virtual prototype alongside the product definition, which was much before the actual design to aid this early software development. Now, creating a virtual prototype needs a lot of manual efforts, which requires modeling of the entire system. So in collaboration with our systems engineering team, we used an in-house tool developed by them to generate the virtual prototype of our next generation audio codec. This in-house tool needs to be given SoC data in a predefined format. Along with that, we have to provide certain dependent libraries. Now, both these are given input to the SystemC code generator. This code generator then parses the SoC data and makes use of the dependent libraries to generate a virtual prototype. This VP is the skeleton source code, and it can be improved by adding more functionalities to it. Now let us see what is there inside the virtual prototype. If you follow the legend here, the blue bar indicates the models that were either generated by our in-house tool or first functionally hand-coded. The orange bar denotes externally available vendor IP. The gray bar shows those models whose functionality was not targeted, hence they are black boxes. So our in-house tool uses SoC data and dependent libraries to generate the interconnect bus fabric, the register math, and black boxes of all the design sub-blocks, along with appropriate connections. We can then develop individual models and instantiate them in a top-level wrapper. Now, this top-level wrapper can be further instantiated in the test bench, along with necessary clock and reset connections. The external vendor IP can then be connected separately according to the design specifications. Now, if you see this test bench block here, you would notice certain blocks labeled as agents, like this UR agent, I2C SPY agent, and I3C agent. These are SystemC agents, much like UVM agents that provide connection and data exchange with peripherals in absence of an actual physical device. This complete code is then integrated and built together to generate an executable, which is shown here as vp.exe. So to run an application, the executable can be launched and the application alpha file should be provided as an argument to it. Now, I'd like to show you the bird's eye view of the complete system in order to better understand how the virtual prototype is used by the software team. If you notice this block here, it's labeled as remote PC or host PC. It is an external system which could be at a different location, but it is able to communicate with a host PC over internet. This is the host PC which runs the software testing framework. Now, this is a framework which is capable of configuring application code either by receiving it from the remote system or this remote PC, or by generating it locally using some scripts. This block is the debugger. This can be used to build and launch applications in debug mode. The debugger also interacts directly with the system under test, which is the virtual prototype or an FPGA or silicon. And it also monitors the ports of the system. Now let us see how the application control flow works here. The remote PC sends application parameters to the host PC. The software testing framework running on the host PC then configures the application, which is then built by the debugger. The system under test then executes the application. The debugger, which is monitoring the ports of the system under test, then returns results to the host PC. Now, the software testing framework again analyzes and returns these results to the remote PC. The remote PC can then report an application test, fail, or pass status, depending on how it analyzes those results. Now, pay attention to the yellow arrows here. The remote PC, the host PC along with the software testing framework, and the system under test can be clubbed together and called a unified testing framework. This is a common testing framework to run applications seamlessly on different platforms, whether it be a virtual prototype, an FPGA, or silicon. I shall cover details of this in the next slide. Please look at the green arrows here. The debugger, along with the system under test, can be clubbed together and called the software debugging system. Now, software debuggers are very useful tools. Application debug is very easy with a virtual prototype while it interacts with a debugger. The virtual prototype executable can be launched in a wait or debug mode, and a debugger can be launched separately to run the application in debug mode. The application then attaches to the waiting executable, and then it can be run interactively. The breakpoints can be set in both the application code as well as the VP source code. And we can switch controls using those breakpoints in order to review desired application scenarios. So that way, anybody can debug both the application code and the virtual prototype source code together. Now, this is a very positive aspect of virtual prototyping and an extremely powerful debugging feature. For hardware-software debug in a virtual prototype, as compared to silicon or FPGA, there is much more visibility. We used Visual Studio to build the executable, hence it was very easy for the software folks to navigate and debug. This entire system proved to be very helpful in the early development of the software testing framework itself. As in the last slide I mentioned, the unified testing framework can run applications seamlessly on different platforms. Here is the description of how it interacts with the virtual prototype. This here is the test server. It is basically the host PC that runs the software testing framework. Now it connects to the SystemC agent present within the virtual prototype using a TCP/IP-based firmware. This firmware was specifically written to have the testing infrastructure interact with the virtual prototype. Now, how the flow works is, The testing infrastructure or the software testing framework, it sends information over this TCP/IP firmware to the agent, say for example, the UART agent. And it sends information to configure an application that would validate the I2C communication subsystem. Similarly, the test server could also send information to an I2C agent in order to configure an application that could verify the UART communication subsystem, or for that matter, any other communication subsystem or other design blocks. So the unified testing framework supported early software testing and validation. Since it is software-based, it was very flexible for the software team to use. The team would only have to configure an application once, and then it could be used across multiple platforms. It also supported single block validation. Now, since the executable can be configured in different scenarios and launched with different applications, it supports multiple parallel users, which is not the case with an FPGA or with a hardware accelerator or even with silicon. So basically, the entire subsystem and the design blocks could be validated just by sending information to various agents present in the virtual prototype. Our quantified simulations showed 1000x gain in simulation speed. Now, this data is from the same application which was run on both the RTL as well as the VP. As you can see, the CPU time for a virtual prototype simulation is a mere 30 seconds, whereas for RTL, it is over 300 seconds, which clearly indicates how beneficial it is to aid in device driver development. This guy here is clearly happy about it. So talking about the benefits of virtual prototyping for software validation. The simulation speed. Like I mentioned, it is extremely fast. So where system timing accuracy is not a concern, virtual prototype presents as a very good alternative, which is why it turned out to be a great platform for early device driver development and validation. For complex application scenarios, this gain was even better. The ease of usage. Now, the virtual prototype is built in SystemC, inherently C++, which is easy for a software person to navigate, debug, and use. And the source code was built in Visual Studio, which the software team is more habitual of using. As explained before, debugging of application code becomes a cakewalk as compared to the hardware-software debugging challenges that come with hardware accelerators, FPGA, and silicon. The virtual prototype made a significant impact on the software development and validation schedule by giving a 3+ months head start. The VP development was completely agile and aligned with the software schedule. It was done in phased releases. So we analyzed the software development plans. We picked the design blocks that they would go to develop and validate first. We build those models, we test them at our end, we review the features and functions with the software team, and then we make a launch once okayed. So there were multiple phase releases of the virtual prototype so that all the development and validation was always in sync with the software team. Now, we developed a lot of IP for this virtual prototype, but we also reused a lot from various other projects. So the development process was fast, and it would continue to be that way with more and more component reuse. To conclude, I would say that in our current project, we were able to pull in the software development schedule by 3+ months. And for more complex designs, we estimate the gain to be of the order of 6 months or more. Now, imagine being able to see how a product would work in various scenarios, even before the product is actually designed. It gives a sense of understanding of the product, thereby boosting confidence in it. But aren't we all doing this in our daily lives? I mean, we try three-dimensional images of furniture in our rooms before buying it to see how it looks. So by qualifying the design behavior using a virtual prototype, we can provide the same confidence to our customers. For future work, we are exploring virtual prototyping for architectural analysis of designs with more complexities. We are also exploring algorithm profiling, and a lot of in-house automation is being done to make virtual prototype easier to create and use. So in summary, virtual prototyping typically offers a solution for early system testing, but we applied it in getting a head start for the development of hardware-dependent software. In addition to early performance and architecture optimization, virtual prototype also enables a shift left of the entire verification and validation process. As a result, firmware and application software tests can be carried out much earlier and parallel to the hardware development. In the future, fast virtual product releases will move many other processes step up that were previously only possible once product development was completed. Thank you very much for listening. I'm okay to take questions now. Thank you.
Hello, I'm back. Are your cameras working? Can you hear us?
Yes, yes, I can.
Awesome, awesome. We do have a question from the audience. I DM'd you part of it.
Yes.
Jonathan from Qualcomm, if you want to unmute, you can feel free to ask Shweta your question.
Hi, Saxena.
Yeah.
I have a question about how you handle late changes to the analog registers for the analog blocks in the software development. If we force the analog guys not to change their registers, they will likely have to add a lot of extra spare registers, wasting silicon, power, stuff like that, that will ultimately wind up not being needed. So, you know, if the software cannot automatically, software team cannot sort of automatically accept the sequence changes when the analog design is finished, maybe even after testing on the bench for the final settings, right? Then you would have to keep retesting the software development, which I'm told already has more people than the actual analog design team has for a given project. Is there a place for PSS in this flow?
Yes, it can actually coexist with PSS. And as for your question, so basically we have it in-house automation tool that generates the skeleton of the virtual prototype to after every change in any register map definition, right? So it is basically we are referencing to that source code and we are building in nutshells. So whenever there is an update, there is change not to the skeleton code, but to the nutshell. It is still some amount of work, but it is not a great deal of work because of that automation process, that the framework that we have created for it.
But can the software take the information, the updated information in PSS?
Yes.
And regenerate their, driver code? So
let me explain it this way. If you're talking from the perspective of using the resources, the software team, the DV team, we are using the common resources, whether it's for the referencing to registers, whether they're referencing it in the device driver code or they're referencing it in, we are referencing it in the DV environment. So it's the same source. So they are not regenerating the device driver code. They are basically testing the device driver code, writing the code and validating it with this model. So
okay, I was
yeah,
thinking that the sequence information in PSS for a given action could be directly translated into driver code for that action, right? That's what I, that's
Yeah.
where that's where I'm seeing an opportunity.
Okay. Okay, I see. So basically, we have tested some of our virtual models using the UVM SystemC standard, test bench using UVM sequences, and validating the models using those. And also, like when it comes to the device driver developments for the software folks, they're also reusing it from different projects, right? So it's like if there is a change in the device driver, it is usually minor, but the validation of it has to wait until and an FPGA is set up. But using this, they don't have to wait for small changes, validation, wait until that time. They could do it very early in the design cycle. Did that answer your question?
Yeah, I think so. So
Anyone else have any questions? Feel free to just unmute and ask your question.
I had a quick question. So you're using like a TCP protocol, and then how is the agent actually connected to your prototype? Are you using like TLM transactions?
Yes.
There?
Yes.
Okay.
Yes. TLM transactions. Yeah.
And then like I saw a clock in there, so this is all timed, and you're using the timed function.
So
Or just to
I'm sorry.
pretend like you're utilizing time, or you can strip that out if you want to use this as a verification tool, like on your emulator, and not want to have it consume time.
So the client server TCP/IP based client server model is basically just a C++ application, and it was written specifically to have the software testing infrastructure interact with the virtual prototype. The infrastructure is basically common to the FPGA and the silicon, but to use the same thing on the virtual prototype, this application was written for it to interact with the VP. So the same test suite that the software has would run seamlessly on the VP, on the FPGA, and on silicon. Just the physical interaction would be different. The VP would interact through this application, and well, with the FPGA and silicon, we have physical connections. So that was the purpose of it.
So anybody else got any questions? This is just a friendly reminder that these people put a lot of work into their papers. So please go and vote. We're going to be giving somebody large sums of cash, not really that big of large sums of cash, but there is cash involved in about an hour. So after this presentation, there's about 30 minutes where they tally all the votes. They check the hanging chads, for those of you that know that reference, make sure all the ballots are correct and valid. So please go out and vote. It'd be really useful.
It's really commendable, people attending the presentation at this point of time after such a long day of a lot of knowledge from everywhere.
Yeah, you missed it.
Thank you.
The other two guys are from, you're US, right? You're in the US?
Yeah.
The other two people are from Europe. So they're like midnight, 1 o'clock in the morning.
Yeah.
Go vote for their paper, people. Go put some votes out there. Well, thank you, Shweta. Did I say that right, Shweta?
Yes, you got it right.
Okay, thank you. I was like, oh crap. The one person I wanted to make sure I knew how to pronounce.
I tried changing my name. I couldn't change it. So I tried a couple of times.
You can change, you can't change it with the more. You can go to, if you click on your name and go more and
so I'm using rename. It doesn't give me an option. I don't know, maybe because I don't have Zoom installed. Like I'm using the desktop or the web.
Oh, that's probably what's going on. Oh, okay.
Yeah.
Well, thank you so much for presenting today. We really appreciate it. And answering questions, and awesome. Thank you so much.
Thank you.
All right. We have 1 minute. So we have 1 minute till we have to start again. Actually, not even that long. So everybody, please go out and vote. I'm going to keep saying it. I'm going to harp on it. It's going to get annoying. So we're going to move on to the next presenter. Juan Santana is a part of the virtual systems development team in the Fraunhofer Institute for integrated circuits in Dresden. He's currently working on system level modeling, HIL, test and validation. Electronics, he has electronics engineering from the Universidad Industrial de Santander in Colombia, and a master's in micro systems and micro technology engineering from, I'm not going to pronounce that, from German Institute. Background in embedded system and applied electronics in the fields of robotics and unmanned vehicles. Please, everybody, welcome Juan Santana's presentation, evaluating the feasibility of RISC-V core for real-time applications using virtual prototyping.
Hello, everybody. My name is Juan Camilo Santana. I am part of the Fraunhofer Institute for Integrated Circuits, Division of Engineering Adaptive Systems. We are located in Dresden, Germany. As a member of the Virtual System Development Group, we continuously work and provide services in the fields of system-level modeling in System Verilog, SystemC, and SystemC AMS, verification at RTL and system level, fault modeling and injection, hardware in the loop simulation and testing, development of customer-specific design flows and interfaces. Today, I would like to present our publication titled Evaluating the Feasibility of a RISC-V Core for Real-Time Applications Using a Virtual Prototype. Before I start, I would like to highlight that the methodology is being developed in the framework of the Europe Union-funded project Value 3S, in cooperation with Siemens, where Siemens is the use case provider. In the next slides, I will guide you through the proposal of this work in progress towards the proof of concept. The replacement of a key component within industrial embedded systems usually requires huge verification and validation efforts, especially the replacement of the MCU core architecture. Normally, this entails significant changes to the hardware-software co-design and co-verification process, possibly including the purchase of costly design and verification IP. To briefly recall the production or prototyping of an industrial-grade electronic device like an ECU, first, product device requirements and specifications based on customer demands are set up. Then, the system architecture is defined. From this, a selection of components that meet the specification is done. Between them is the MCU, microcontroller unit. With this known, the software development team could start. Also, the hardware development team could start both with software and hardware design. At the end of the verification and validation process and several iterations of these two stages, software and hardware, to meet the requirements, hardware and software integration will be done, and last refinements to the device as a whole will be carried out for delivery. In the case in which a system redesign takes place where the established MCU core is replaced by another core, like for example RISC-V core, since the complete redesign requires a significant effort, a feasibility evaluation study helps to elaborate the system requirements and to detect possible issues early in the replacement process. Based on this, we propose a hardware-software co-verification methodology to evaluate the feasibility of an MCU core replacement based on a virtual prototype. The virtual prototype will support the software porting or the software redesign and the adoption, and also the hardware exploration or the part of hardware redesign, thereby saving time and cost for the redesign process. This methodology links the virtual prototype development process with the requirements management process to reuse the test cases and prove how feasible is the system upgrade. RISC-V, an open source instruction set architecture, has gained lots of attention in the last years. The foundation of any computer architecture, microcontroller unit, or microprocessor is the computer language, called instructions. The computer vocabulary is called the instruction set, that is RISC-V, and this has been intensively developed, implemented, and promoted in the commercial and as well in the educational field. Consequently, this has led to a wide range of available tools, including software tool change like ADEs and profiling tools, simulation and prototyping tools like instruction set simulators and custom instruction extension generators, or also debuggers, hardware implementations and hardware devices like cores and system on chip full implementation, and even silicon devices and development boards. Verification frameworks for hardware design at RTL level. Many of these tools and developments come into play for rapid system prototyping, where the application of virtual prototypes is advantageous due to their flexibility. Here it's important to highlight that many of these tools, designs, and models are freely available, giving us our time flexibility at the moment to adopt them. The RISC-V adoption, and just to mention some tools used in this development flow, could be simplified too. An IDE to write code to target RISC-V that includes a RISC-V GCC compiler to generate machine language, to later call a RISC-V linker to generate the binary executable file. This file is used to program the memory of a physical device or to load the application in the virtual prototype. Then, when we load or execute this application in the virtual platform, in this example, the virtual prototype will generate a representative text output in the command line during the execution. In the same way, we could use this executable application file in a real development board. The virtual prototype in the console text output is analog to this board with the blinking LED. Our methodology is based on a virtual prototype, but what is a virtual prototype? A virtual prototype is an executable software model of a hardware system that runs on a host computer. It simulates hardware at the level that is relevant for the software. CPU instruction sets, memory, interrupts, registers, and functional peripherals are part of it. As such, a virtual prototype provides a functional representation of the target system on which binary program code can be loaded, executed, and debugged, in the similar way that the software developer uses a development board. Normally, virtual prototypes are models with reduced accuracy in comparison with RTL, usually written in C++, C, C++, SystemC, or SystemC AMS. Virtual prototypes are used by and for software developers to support development phase and test cases, to do the software design, to extend or elaborate the platform application interface, to develop and detail drivers. Change of the core in a microcontroller unit not just represents a hardware change, it also involves significant changes in the software domain. Software toolchain adoptions are needed as shown previously. Applications has to be ported to the new MCU. Functionality of the application for the new microcontroller unit has to be validated. Besides supporting the hardware model refinement in the virtual prototype, the software development team is enabled to move earlier with the software adaptations and tests. Virtual prototypes are used by hardware developers for architectural exploration and performance estimation, also to refine the hardware design, to do the performance estimation, and to get some time in verification. The advantage of virtual prototype include hardware-software co-design, supporting software developing tasks by adding more hardware details to increase the modeled functionality. This expands the ability of the system designers to do hardware architecture exploration and its trade-off. Virtual prototypes also have advantages like they are early available in the development process, they are easy to set up, they are easy to extend, for example, by SystemC, they enable fast simulation of the full system compared with RTL, and they reduce the hardware dependency. The nature of the virtual prototype extends the so-called prototype test bench for the software development team. With a virtual prototype, the hardware dependency almost vanishes in the first stages of the project to prove the viability and the concept. A virtual prototype that allows interdomain simulation represents a support tool for software development and updates in a product lifecycle. In this development flow, they can even support full stack software development. Going beyond the pure instruction set simulator, the model can be extended to an interdomain simulation by orchestrating sensors, actuators, and other related parts of the system which are not purely in the electronic system on chip hardware domain. In the classical design, hardware-software flow, most of the software development relies on hardware availability. This normally takes considerable amount of time. With a virtual prototype, software can start to be developed as soon as the first model version is available, even when no hardware design is yet specified. Also, at RTL level simulations of this size take too long. This is where we can see a shift left in the classical flow based on the virtual prototype. Before describing the proposed methodology, I will shortly mention the use case in order to dive into the next steps. Our use case, as shown here, is a motor controller system composed by an electronic unit with a microcontroller that implements a field-oriented control algorithm, which interacts with the plant. In this case, the plant is a permanent magnet synchronous motor. From the microcontroller unit, PWM signals are the stimulus to control the motor movement. Registers are mapped to the analog inputs that represents the motor shaft position and currents in the motor coil. These are used to monitor and sense the motor. This creates a feedback loop for the control application. Tight time interaction between the control software with the peripherals and external system components imposes real-time constraints on this system. Due to a hierarchy of timing requirements from the permanent magnet synchronous motor system, from the application down to the embedded system, the control algorithm must run within a cycle time in the magnitude of microseconds. In order to verify and validate the feasibility of replace the legacy core by a RISC-V core, we have structured the following methodology. With the proposed methodology, first we map the available requirements. Then we build an untimed virtual prototype reusing existing model IP blocks. Then we make the porting software application. The hardware virtual prototype integration is composed by several modules. First, it starts with the instantiation of the RISC-V core instruction set simulator, and this besides a RAM model. Then, some peripheral models are added to achieve the basic functionality. These are interfaced to the instruction set simulator using a transaction-level model API. At this hierarchy completes the virtual microcontroller unit. Towards to complete the complete system hardware, some external models components are added, such as the permanent magnet synchronous motor model. This hierarchy level is the virtual system. And finally, one level above is the wrapper, which instantiates and calls the previous blocks. Also, it is on charge to configure and control all the simulation parameters like start, stop, duration, and linking or loading the application executable. The last piece in this formula comes from porting the existing field-oriented control application software to the RISC-V virtual hardware. This demands the adoption of some of the existing drivers for the virtual prototype in functions where a RISC-V instruction subset is implemented by the instruction set simulator. Compiling the firmware is reduced to the point where the RISC-V GNU software toolchain and the compiler options are matched to the target the architecture supported by this instruction set simulator. Taking advantage of the SystemC nature based on C++, the simulation runs based on the model executable and calls the firmware application as an executable argument. This executable is refined taking advantage of the framework previously described. In the way to prove the concept, some models of the peripherals are reused from the existing system. The block systems are interconnected via SystemC TLM transaction level modeling. The instruction set simulator wrapper instantiates a RISC-V core. As basic requirement for this virtual prototype system on chip, a timer-based interrupt is included in this model. This supports the time base for the real-time operating system that runs the firmware application. One level above, this creates the base of the virtual prototype that will support the test bench for the time metrics to be acquired. Using TLM, the firmware has access to the values of the motor model, current, voltages, position, and speed. This platform serves as the basis for the proposed test bench. Continuing with the proposed methodology, we perform a timing characterization of the existing system. For this, we need to split the system architecture hierarchy in order to interface the virtual prototype with the test bench. With the aim to simplify the timing annotation of the implemented virtual prototype, the analysis of the system starts on a very high level. Here, we will focus and look at the interaction between the unit under test that is composed by the virtual prototype and the motor to get metrics related to the behavior of the motor controller by using the PWM as output and motor stimuli, and the encoder and analog signals as inputs and feedbacks for the controller. The specification on this abstraction level helps to define timing metrics and test cases. The basic functionality of this unit under test is receiving basic user actions to control the motor, for example, start, stop, accelerate, and brake. Send PWM stimulus to the motor according to the requested action. Analog to digital conversion of the signals between motor and the unit under test and storage them in registers. Reporting of the motor status by the unit under test depending on the received information. This unit under test also has to be aware of time in order to process and output the PWM signals. This timing reference is also an output of the unit under test in order to properly verify the response time requirements. Given the high level of detail of the prior system, system-level verification for this particular challenge has to rely on verification results and measurements of it. This will be the reference metric for the new system, obtained by response time measurements of the unit under test in different test case scenarios and regression runs. We are particularly interested in measuring the response time from interrupts actions relevant for the system reporting the motor state. With the same structure, the test bench will implicitly exercise and evaluate the RISC-V core without diving into the core details yet. In order to realize the timing characterization, a UVM SystemC test bench is applied to the legacy unit under test. The UVM SystemC test bench will be on charge to run each of the test cases implemented according to the system test case specification document, following a common strategy, which consists of the following tasks. Configure the motor parameters using constrained randomization. Take the motor to the desired states. Send a sequence of actions separated by a constrained random time. Monitor the desired response times and send them to the scoreboard for further analysis. After implementing and running the complete verification suite, we can get a profile of the response times for each test scenario. The proposed workflow for the new unit under test reuses several artifacts from the previous design project, especially the system requirements specification document as well as the system test case specification. For the latter, an addition of the timing metrics, timing data from the legacy unit under test has to be done. To conclude the application of our methodology, a requirements-driven flow is taken in account as follows. In the requirements engineering domain, both system requirements specification, and system test cases specification documents are described using a requirements engineering tool that allows to create and verify relations between system test case specification and system requirements items. Each test case contains the expected response time metrics, which are used to verify the system with the new core and report the test status, pass or fail. This information is included in each UVM test case implementation. Here, the UVM test bench runs over the virtual prototype developed. Also, the test suite can be triggered from a continuous integration tool, which reads the status of or each test run represented. Finally, the pass-fail results are sent back to the requirements engineering tool. When a test of a regression fails, it is marked as such in the requirements engineering tool, and a defect or issue or bug must be created and linked to the system test case. This allows to have a complete and traceable status of the project inside the same tool. As described previously, the requirements management flow is linked as follows. System requirements specification and system test case specification are described and taken from Polarium. They are used inside the UVM SystemC test bench that is applied to the virtual prototype. Using a continuous integration tool like Jenkins, the score and results from the UVM test bench are reported back to the Polarium test records as pass or fail. With this last step, we concluded the presented methodology in order to validate the feasibility of a RISC-V core replacement in a microcontroller unit based on a virtual prototype, keeping the efforts still in a low level and a high abstracted system. The link of the requirements flow helps to reutilize and accelerate many of the test cases and the verification and validation methodology at this level. To finalize, here we have presented a methodology based on a virtual prototypes that simplifies the hardware exploration process when running real-time application software. As a result, the obtained platform allows hardware validation at early stages with joint software execution and close analysis between both domains, hardware-software interaction. That reflects performance metrics for the application, software like timing, control loop frequency, and interrupt handling to match the real-time ability of the system. The virtual cyber-physical system helps to identify issues with the application software and the hardware architecture long before an intended redesign. Reuse of the test cases through the concept exploration phase allows to continuously refine requirements and generate test benches for a test framework. This could be reutilized for the next stage for RTL design verification as a golden reference, and it could extend the coverage matrix with system-level stimulus. Within a classic design and verification process, any change of this extent will potentially lead to many failed test cases of a regression, and thus other verification goals, like for example, structural coverage, will not be achieved. The presented methodology shows how the viability of the new concept could be evaluated, while still complying the system requirement specification. At the end, it is important to remark that this is work in progress and is currently under development in the frame of the EU-funded project Value 3S. With this, I have reached the end of this presentation. Thank you so much for your attention. Now, I will be happy to answer your questions.
Does anybody have any questions for Juan? Juan, if you can, yep, you unmuted and are visible now. We know you exist.
Okay.
Does anybody have any questions? I didn't see any questions come over the
Are
chat.
you just doing like pass fail, like a rec tracer kind of thing? Or are you using like the UCDBs in your Jenkins run? Are you tying that to like some sort of coverage database for whether or not that those tests are passing or failing?
That's the idea. So I'm not in
Scripting
charge
a
of the
sim log,
verification.
or
Sorry?
yeah, like, are you scripting a sim log, or are you actually like using a UCB to and tying those pass fails to, like, if the SystemC met all of the parameters, then that would, you know, pass that cover group or something?
So as far as I know, because I'm not related directly with the verification phase, there is a scoreboard, and there is for example, for the analog cases, because we are handling a motor controller here, we have some boundaries for these signals, and the scoreboard is matching these signals in between the range, and then it's generating the pass or fail. What is directly doing Jenkins, apart from reporting, is not on my knowledge at the moment.
Okay, thank you.
You're welcome.
Does anybody else have any questions for Juan today? Also, please go vote. There is 32 minutes till go time. So, but we need questions. Anybody got any questions for Juan, or was his presentation a really great presentation, man? Well, if not, I think we will end it here. Please, everybody go vote. Juan, thank you so much for your presentation. I don't want to clap too loud because on the mics it gets bad, but thank you so much for staying up and being around for Q&A. Stick around to see if you won Best Paper. And everybody, thank you guys so much for coming to our presentation in DVCon. And hope you guys can join us for the presentation of the Best Paper Award, or join us and gather. And if you have any questions for Juan or any other presenters today, you can maybe hit them up and talk to them there. Thanks everybody, and you guys all have a great good morning, good evening, and good night, depending on where you're at.
Thanks, Josh. Have a good day to you too.